Okay, everybody, define the natural logarithm using an integral. This is an easier way to define the logarithm, and it's what I would do if I was asked to compute log of 3, for example. Define the log of some number x to be equal to the integral from 1 to x of the function 1 over t dt. I'm just making up a new variable name. What this means is that we want to look at this function this is the graph of the function 1 over t, or 1 over x, or whatever you want to call it, and somewhere is 1, and so it's just, if this is x, then it's this area. Okay, and if this was x, then it'd be a bigger number. If this was x, then it would be this, but counted as negative area, because we're going to the left. So this is, think about this, is single variable calculus. Very good to remember this. Okay. This works for any x in the entire positive real numbers. Okay. It doesn't quite work for 0, for example, because this graph just goes up like that, and it's not really clear if there's finite area, and there's really not. So, but anyway, this is where it works. And so now we have a function called log, natural log. Some people call it ln. And it takes any input which is a positive real number, and it'll spit out a real number. It's not obvious, but in fact you can get any real number, all as negative as you want, by going with x closer and closer to 0, and as positive as you want as the output, the positive value, if you just take x farther and farther positive. Anyway. Okay, it doesn't quite work for complex numbers. How does this work for complex numbers? Well, it's interesting to think about that. That's called complex analysis, and it's a wonderful class that you could take. Find a power series formula for these things, which are basically going to all allow us to compute the same values of log. We'll be able to compute log of 1. Well, that's 0. But now we'll be able to compute things like log of 1.1 and all the way up to log of 1.9. We'll be able to compute log of 0.9 all the way down to 0.001. Or we'll be able to get everything in a little disk around log of 1. So let's see how that works. So the key is that the derivative of log of x is 1 over x. And so in particular, actually this one will be the easiest one to start with. So let's start with that one. Easier. The derivative of log of 1 minus x will be 1 over 1 minus x, and then the chain rule will bring a negative 1. Chain rule meaning we have to take the derivative of the inside function minus x becomes a minus 1. Okay. Single variable calculus. Now this is just, let's just have that minus 1 hang out, and so now we have geometric series. And we've proved that this is 1 plus x squared plus x to the third, by which we mean the limit of the partial sums of this series, of this infinite series. Okay, well, that's the derivative. So the derivative of log is this. Well, the derivative of log of 1 minus x is this. So now, first of all, let's observe that this has radius of convergence convergence. X between -1 and 1. Okay, centered, it's a disk centered at 0. In fact, we could take a complex number, so radius of convergence, any x in an element of the disk of radius 1 about 0, the complex number 0. Okay, and we know that because geometric series will converge whenever the absolute value of x is strictly less than 1. And that is what we mean by disk of radius 1. Okay, so if you need to, review the geometric series. Okay, but now let's use it. So now we integrate term by term. These are polynomials. It's really easy to integrate x to the third. It's x to the fourth over 4. Term by term. People say this, integrate term by term. What they mean is the 1 becomes an x. The x becomes plus x squared over 2. The x squared becomes x to the third over 3. And in general, this infinite series formula becomes another infinite series formula, namely x to the n over n, where now we have to start at n equals 1. Okay, this is actually important now. We're not just asking if it converges or diverges. We know it converges. We know exactly where it converges. What we care about is now the particular value that this be equal to, I guess, log of 1 minus x. Okay, we integrated this side, so we integrate this side, and so that's how we get log of 1 minus x. Oh, and I forgot this minus 1. That is super important. So, because otherwise my answer would be completely wrong. It would be minus the answer. So I'll put this minus sign. Okay, so this is interesting. Now we have a formula. And this valid when, well, the same thing, x strictly less than 1, just like the geometric series. Because when we integrate term by term, it doesn't change the radius of convergence. We could check that if we liked. And another way to say this is that x can be in a disk of radius 1 about the center 0. Okay. You could think x minus 0 is strictly less than 1. Okay, so it wanted some other things. Now we have this one. Check. What next? Well, how about this one? Okay, log of 1 plus x. Log of 1 plus x. So I guess if we took x equals minus x, will that work? Let's see. Let's replace an x with a minus y, okay? Then what will we get? Well, we will get log of 1 minus y. In other words, 1 plus y on the left-hand side. Now, what will we get here? Well, the minus y will replace the x. So we'll get minus y to the n. But that is, well, let's start at n equals 1. Now that is minus -1 to the n. So it's alternating. Oh, we get an alternating sum. Okay, and then let's just bring that in and just get one more of these net minus 1s. -1 to the n plus 1. There's just one more of them. And let's make sure to start it at the correct value. Okay. And so in other words, let's write out the first few terms. This looks like, well, n equals 1, y minus y squared over 2 plus y to the third over 3 minus y to the fourth over 4 plus etc. etc. Okay, so we can start to see some of the partial sums would look like. Okay, well this is great. This is now a formula for log. And now where is it valid? Well, all we did is we flipped everything by a negative. Now let's view that disk. Here's a disk of radius 1 about the origin in the complex numbers. And all we did is we took x and put it to minus x. We just flipped everything. And in other words, the disk went back to itself. And so because this was our transformation, this is valid, valid for all y in the exact same disk. Okay. And so we have one more left to do. So we've done this one. I can call this variable whatever I want. So I called it y. Let's do this one. Log of x. How do we get log of x? Or log of just a number. Well, okay, let's make another coordinate transformation. We want that just to be the number. Okay, so let's just call x equals 1 plus y. All right, well that means that, that y is equal to x minus 1. Okay, so log of 1 plus y becomes x. This is called a shift. So in other words, I am shifting this thing over here. And now it'll be valid over here, which is a circle centered at 1 in the complex plane. But anyway, so this is a shift. That gives me log of x, and now this, I have to replace the y. This y becomes a x minus 1. And so we're just centering at 1. Okay, so the same sum, 1 plus 1. Now I have y to the n becomes x minus 1 to the n over n. Okay, n should start at 1 and go to infinity. And let's write out some of the partial sums. The partial sums look like x minus 1 minus x minus 1 squared over 2 plus x minus 1 to the third over 3 minus x minus 1 to the fourth over 4 plus blah, 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 blah. So you can see the first partial, the second partial sum, the third partial sum, the fourth partial sum. Okay. Well, that's great. Now, where is this valid? Valid for all y, for all x is my variable name, in a disk of radius 1 about the number 1 in the complex plane. Okay? In other words, that picture. Okay? Now, what I want you to notice is that all of these formulas allow us to compute the exact same values of log. Like, we just shifted around the inputs a little bit, but you see that, like, we can compute log of 1 because x was 0 here, and we get 1. X was 0, we'd get 1. We can also compute log of 1.1 using this. We can compute log of 1.2 all the way out to log of 2 we can't quite get, because it's not guaranteed to converge on the boundary of the disk. But we could get log of 1.99 maybe. And you see that to get 1.99, x would be 0.99. Here, x would be negative 0.99, and we'd get the same value. And over here, x would be 1.99. So you see that if we plug in 1.99 there, if we plug in negative 0.99 there, and if we plug in positive 0.99 there, we're getting the same number. And so we're just, none of these is any more interesting than the other. They've just shifted things around a bit. Flipped things. So that's interesting. That's all.